Hidden inside this old power plant in Virginia, Minnesota are some pretty unusual machines. Steam turbine-driven blower fans, complex coal stoker controls, and even a Ford engine powering an air compressor. Hello, I'm Jason from Steam, Electricity, and Propulsion. In the first video, we saw an overview of this plant, but now we're going to dig into how everything actually worked. This power plant was built in 1922 and was modified and expanded over the years. Today, the plant contains equipment ranging from the 1950s to the 1970s. The draft fans are designed uniquely with a motor and a turbine for power. The forced draft fan on the Wix boiler uses a 43 horsepower Terry turbine with a reduction gearbox to lower its speed from 4,000 RPM down to about 1,200 RPM. The turbine uses a hydraulic variable speed governor which can be adjusted with this valve. Instead of traditional fly balls, a shaft-mounted oil pump supplies pressure to a hydraulic piston, which controls the turbine speed. The induced draft fan on the Erie City boiler also uses a Terry turbine, and here you can see the reversing buckets used to redirect steam. Airflow was automatically controlled by this pneumatic actuator connected to the dampers. At the bottom is a pneumatic relay that uses signal air and a pilot valve to control the piston. To see fans like this operating, let's look at some at the Hibbing power plant. Now let's look at a rare type of boiler, a Riley boiler with DC powered stokers. Direct current is supplied from the battery room. A rectifier produces about 120 volts of DC. This control panel regulates power to the coal feeders, which use these gear-like rotors to crush and meter the fuel. The rotary beater which spreads coal onto the grate is powered by an AC motor using this variable speed pulley.
Can you turn it back now?
A spring presses the flanges together while belt tension pushes them apart. On the Wix boiler, one motor can power all 4 stokers through a drive shaft. Like the Riley stokers, a variable speed pulley adjusts how far coal is spread across the grate. The motor and pulleys are shifted vertically with this screw knob. Each stoker is driven through a clutch and chain connected to the shaft. For redundancy, a turbine was installed on the other side of the shaft, something rarely seen today. This machine is a Carling turbine, which I got a diagram for. At the Hibbing power plant, they occasionally burn coal in a similar boiler. Down by the circulating pumps, coal from the dump pit is carried upward in this bucket elevator. At the top of the plant, conveyors distribute the coal into any of the 3 bunkers. This large machine removes coal from the belt, directing it into a bunker. The Riley boiler has a unique layout. The economizer and air heater had to be installed on the left side of the boiler due to size limitations. The draft fans are directly above, and the electrostatic precipitator is on the boiler outlet instead of after the heat recovery units. The superheater on the Wix boiler can heat steam to over 1000 degrees Fahrenheit, but at 600 psi, the temperature only needs to be about 800 degrees. Water was pressurized by these pumps by the ash hopper and sprayed into the steam to precisely control its temperature. On the other side of the ash hopper are the air compressors. Because compressed air was critical to the pneumatic controls, this gas-powered Ford engine could drive an air compressor during a blackout. Older plants like this were designed to restart without grid power, while most modern plants rely on the electrical grid to function. We climb up these old spiral stairs into a dimly lit room. Behind this door is the control room. Inside this panel are Bailey pneumatic relays which regulate signal air pressure for the pneumatic valves and dampers. The knobs adjust spring tension against a mechanism similar to a regulator. Today, all this equipment is abandoned, but inside the original turbine hall, there are some 50,000 pound-per-hour Scotch boilers. Fresh water is heated with steam inside this deaerator and is sent down to the feed pumps. This fresh water is supplied by reverse osmosis units in the turbine hall. These three electric-driven pumps force water through the economizer, which captures waste heat from the double-pass boiler. On the boiler's smoke box, there is a pipe leading to the intake of the blower fan. This is an exhaust gas recirculation system which reduces nitrous oxide by cooling the fire. In the back of the power plant is an older O-type gas-fired boiler which also has an FGR system. The flue gas intake damper was manually controlled, unlike on the Scotch boilers. Due to the high boiling point of water at 600 psi, an economizer is necessary to capture exhaust waste heat. The Scotch boiler is running at a 13% load and achieving 83% efficiency with a stack temperature of 380 degrees. The draft fan VFD is running 53 Hz, and there is about 3% extra oxygen going into the fire to ensure complete combustion. These modern boilers supply steam to the district heating system through underground tunnels. Down in the basement, we see steam-powered condensate pumps for the plant's heating system.
What you just heard there, these are steam pumps that pumps condensate up to our new DA tank.
This tunnel goes out to the underground steam lines, but there are no condensate return lines for the district heating system. In the old system, steam was extracted from the turbines. Secondary throttle valves maintained 50 psi of back pressure on the high-pressure turbine and allowed excess steam to pass through the low-pressure turbine. Besides district heating, extraction steam is used to preheat water. First, low-pressure steam heats the shell and tube water heater. The Feedwater pumps can be seen behind the water heater. Steam at about 15 psi is used in the deaerators, which remove dissolved air before the water is pumped into the boilers. In the circulating pump room, these pumps send lake water to the old water softeners, which replace water lost in the district heating system. There is a larger 65,000 gallon per hour system for winter and a 30,000 gallon per hour system for the summer. This old power plant is now being dismantled and it will be closed in October. When it is demolished next year, all this complex machinery will be gone. In the next video, I'm going to Wisconsin to explore the SS Badger's engine room. If you want to see more rare equipment, take a look at this rare coal boiler or the Hibbing power plant.